Hello friends, today we will read about chemical thermodynamics. Chemical thermodynamics. Thermodynamics, the branch of science which deals with the study of different forms of energy, the interconversion and the quantitative relationship between them is known as thermodynamics. Chemical thermodynamics, it is a branch of physical chemistry which deals with energy change in physical and chemical process. Isothermal process. When the temperature remains constant, it is called isothermal process. Adiabatic process. When there is no exchange of heat with the surroundings, the process is called adiabatic process. Isobaric process. When the pressure is constant, it is called isobaric process. Isochoric process. When the volume remains constant, it is called isochoric process. System. Part of the universe under observation is called a system. Surrounding. The rest of the universe is called surrounding. Open system. The system which can exchange matter as well as energy with surrounding. Example, open container. Closed system. The system which can exchange energy but not matter. Example, closed container. Isolated system. The system which can exchange neither energy nor matter with the surrounding. No perfect example has been given. State of the system. State of a system is generally defined as a condition of existence of the system when its macroscopic property have definite value. State variable. The measurable property which are required to describe the state of the system are called its state variable. For example, pressure, volume, temperature, etc. State function. The property of system whose value depend only upon the initial and final state of the system and do not depend upon the path by which the state is attained are called state variable. For example, internal energy, enthalpy, etc. Intensive properties. The properties whose magnitude does not depend upon the quantity of matter present in a system. For example, temperature, density, specific heat, viscosity, refractive index. Extensive properties. The property whose magnitude depend upon the quantity of matter present in the system. For example, mass, volume, internal energy, entropy, free energy. Reversible process. A process which occur in fight seemingly slowly. A reversible process is an ideal process and cannot be realized. Irreversible process. The process goes from initial to final state in a single step in finite system and cannot be reversed. Work of expansion or pressure volume work. W is equal to P external multiplied by delta V. When work is done by the system, work is equal to negative. When work is done on the system, work is positive. Work done is reversible isothermal expansion. W is equal to minus 2.303 nRT log V2 upon V1. W is equal to minus 2.303 nRT log P1 by P2. W compression is equal to 2.303 nRT log P1 by V2 equal to 2.303 nRT log P2 by P1. Work done in free expansion W equal to 0. Irreversible isothermal change Q is equal to minus W equal to P external V final minus V initial. Adiabatic process. Delta U is equal to V W adiabatic process. Law of thermodynamics. Zeroth law. If A, B and C are three distinct bodies and A and C are in thermal equilibrium with B, then A is also in thermal equilibrium with C. First law of thermodynamics: energy can neither be created nor destroyed, but it can be converted from one form to other. Delta U is equal to Q plus W, where delta U is the change in internal energy, Q is the heat change of system, W is the work done. Sign conversion. Sign convention. Heat absorbed by the system is positive. Heat released by the system is negative. Work done on the system is positive. Work done by the system is negative. Statement of second law of thermodynamics. Clausius statement: it is impossible to construct a machine that is able to convey heat by a cyclic process from a colder body to a hotter body unless some outside agency does work on the machine. Thomson's statement: the heat of the coldest body among those participate in a cyclic process cannot serve as a process of work. Kelvin Planck statement: it is impossible by means of inanimate material agency to derive mechanical work or effort from any portion of the matter by cooling it below the temperature of the coldest of the surrounding object. Third law of thermodynamics: at at absolute zero, the entropy of a perfectly crystalline substance is zero. Important term: heat capacity. The heat required to raise the temperature of a body by 1 degree Celsius is called its heat capacity. It is given by the product of its mass and specific heat units J per degree Celsius. Specific heat required to raise the temperature of 1 gram of substance by 1 degree Celsius is called specific heat. Unit is joule per gram per degree Celsius or joule per gram per Kelvin. Molar specific heat at constant volume, CV. Heat required to raise the temperature of 1 gram of a gas by 1 degree Celsius at constant volume is called its specific heat. Molar specific heat at constant pressure, Cp. Heat required to raise the temperature of 1 gram of a gas by 1 degree Celsius at constant pressure is called specific heat. Relation between Cp and Cv. Cp minus Cv is equal to R. Internal energy E. It is defined as the energy associated with a substance. For its existence, it is equal to the sum of total of all the macroscopic as well as macroscopic energy associated with the substance. Only change in internal energy can be appreciated. Enthalpy H. Change in internal energy represent energy gained or lost by the system at a constant volume. No work included. Change in internal energy is not a very useful term for practical purpose because most of the reaction process occurring in nature are at constant pressure. Therefore, another term has been defined which is called enthalpy. Absolute value cannot be determined, only a change is appreciated. It represents energy gained or lost by the system at constant pressure. Work included. Delta H is equal to W delta E plus del P delta V. If the reaction involves change in the number of mole of gaseous substance, delta H is equal to delta E plus delta N G R T, where delta N G is equal to Np minus Nr gases. Enthalpy of a reaction. It is defined as amount of heat gained or lost when the number of reactant molecule as given by the balanced chemical equation completely react to form the appropriate number of the product molecule. If heat is released, the reaction is exothermic and delta H is negative. If heat is absorbed, the reaction is endothermic and delta H is positive. Standard enthalpy of a reaction delta H degree. It is defined when the component of the reaction are in standard state. Standard state means 1 atmosphere pressure and temperature 298 Kelvin 25 degrees Celsius. Measurement of enthalpy of a reaction. Water calorimeter is used for finding heat change accompanying the reaction taking place in solution. Bomb calorimeter is used for finding out heat of combustion. Enthalpy of formation. It is defined as the amount of heat evolved or absorbed when 1 mole of a mole compound is formed from its constituent element when in the standard state. It is called standard enthalpy of a formation delta H degree F. In most of the case, delta H F is negative. Standard enthalpy of all elements is taken to be 0, and standard enthalpy of formation of any substance can be numerically taken equal to the standard enthalpy of that substance. Enthalpy of combustion. It is defined as amount of heat released when 1 mole of a substance completely burned in free supply of air or oxygen to form the appropriate product. When in a standard state, it is known as standard state of combustion. Calorific value of a food or fuel. It is defined as heat produced in calorie or joules when 1 gram of a substance is completely burnt. Enthalpy of neutralization. It is defined as the amount of heat released when 1 gram equivalent of the acid is completely neutralized by 1 gram equivalent of the base. When any strong base is neutralized with any strong acid, always minus 57.1 kilojoule heat is released. A strong acid and a strong base completely ionize in solution, and the only reaction taking place is the formation of water. Delta H plus OH minus gives water. Delta H degree equal to minus 57.1 kilojoule. If weak acid is taken or weak base is taken, or both weak acid and weak base are taken, the heat release is less than 57.1 kilojoule because some of the heat is absorbed in causing ionization of the weak acid or weak base or both. Enthalpy of transformation. It is amount of heat exchanged when 1 mole of allotrope get transformed into another allotrope. See diamond, gives C graphites. Entropy of fusion meltings. It is the amount of heat absorbed when 1 mole of a solid is converted to liquid at its melting point. Enthalpy fusion is equal to latent heat of fusion multiplied by molecular mass. Vapor enthalpy of vaporization. It is the amount of heat absorbed when a mole of a liquid gets converted into various states at its boiling point. Enthalpy of vaporization is equal to latent heat of vaporization multiplied by molecular mass. Enthalpy of sublimation. The amount of heat absorbed when 1 mole of a substance directly passes from solid to vapor without going through the liquid state. For example, ice, naphthalene, camphor. Enthalpy of dissolution. It is defined as the amount of heat gained or lost when 1 mole of a solute is completely dissolved in the large excess of the solvent to form solution, so that on further adding the solvent no heat change occurs. Bond energy or bond enthalpy. It is the average amount of energy required to break all the bonds of a particular type in 1 mole of a substance. Laplace and Lavoisier law. A B Q's A plus B delta H is equal to X. Endothermic. A plus B gives AB product delta H is equal to minus X exothermic. If a chemical reaction is reversed, the enthalpy change remains the same but with an opposite sign. Hess laws of constant summations. A gives B at delta H1. B is formed by D at delta H4. A produce C at H2. Then C gives D at delta H3. So delta H1 is equal to delta H2 plus delta H3 plus delta H4. Enthalpy change for a particular reaction is the same, irrespective of whether the reaction takes place in a single steps or more than one step. The law is also an extension of law of conservation of energy. spontaneous and non-spontaneous process. A process which happens by itself in a particular direction is known as spontaneous process. Even if the process requires initiation, it is still considered to be spontaneous process. There are many processes in nature which do not occur by itself. Such process is known as non-spontaneous process. Criteria for spontaneity. Overall, there are two factors, enthalpy and entropy. Every system tends to minimize the enthalpy and maximize the entropy in order to undergo spontaneous process. The simultaneous effect of these two is considered in a single quantity, which is known as Gibbs free energy or Gibbs energy. Entropy is defined as degree of randomness or disorder of a system. Greater the amount of disorder, greater is the amount of entropy. For example, when a cube of sugar is dissolved in water, its entropy increases. Entropy has been related to thermodynamics probability of the state of a substance. It means that if a state has a higher entropy, there are more chance of its thermodynamics occurrence. When energy is supplied to a system, there is some part of it which can be converted by the system into useful work. This is known as workable or available energy. The remaining part which cannot be converted into useful work is known as unavailable energy of the system. Entropy is measure of unavailable energy per unit temperature. So S is equal to unavailable energy upon T, or delta S equal to Q reversible upon T. Unit of entropy are J per Kelvin. In general, increase in entropy of a system favors spontaneity of the reaction. A system tends to go from the state of the less entropy to a state of high entropy for a process to be spontaneous. The total entropy of the universe must increase. Delta S total is delta S system plus delta S surrounding is greater than 0. Gibbs free energy. The path of the energy or which a substance can convert into useful work is known as available energy. Available energy is measured as free energy of the system. It is also known as Gibbs free energy or Gibbs energy. This equation is known as Gibbs-Helmholtz equation. This equation is also useful for criteria of spontaneity. Delta S should be negative, or the spontaneous process which proceed with decrease in free energy are spontaneous process. At equilibrium, a reversible process which is in equilibrium is neither spontaneous in forward direction nor spontaneous in backward direction. So delta G is equal to 0. 0 is equal to delta H equal to T delta S, gives T equal to delta H upon delta S. Different case of spontaneity. Exothermic, increase in entropy. Delta H is negative, delta is positive. Spontaneity is spontaneous at all temperature. Exothermic, decrease in entropy, negative of delta H, negative of delta S. Spontaneity, spontaneous at low temperature, non-spontaneous at high temperature. Endothermic, increase in entropy, positive in delta H, positive in delta S. Spontaneity, non-spontaneous at low temperature, spontaneous at high temperature. Endothermic, decrease in entropy, delta H is positive, delta S is negative. Spontaneity is not spontaneous at all temperature. Standard free energy change and equilibrium constant is delta G0 is equal to minus 2.303 RT log K. Standard free energy change and EMF of the electrochemical cell is delta G is equal to minus NFE0 cell.